Find the magnetic flux through a rectangular loop lying near a long straight wire carrying current I equal 20 amps. The current through the wire will create a magnetic field B that can be calculated as μ0 constant multiplied by the current divided by 2 pi r, where r represents the distance from the current carrying wire to wherever you calculate the magnetic field. As you can see, this distance, when you want to calculate the magnetic field at different position with respect to the wire, is something that changes. For every single distance from the wire, the magnetic field will have a different value, which means that when you want to calculate the magnetic flux, you will have to use an integral because the magnetic field is not constant. So remember, flux will be equal to integral of the magnetic field B dot product the element of area dA. Now, in order to solve this integral, you have to find a small area through which the magnetic field may be considered approximately constant. We are going to consider a sliver of area here that is very thin, such that this dx is negligible when the magnetic field changes over it. And this area will have a thickness dx and will have a height equal to 10 centimeters, or let's call it y. This area is at a distance x from the wire, and just so we can write the dot product for the flux, the magnetic field in this case is into the page because the current through the wire, which is responsible for creating the magnetic field, creates a magnetic field going into the page on this side and out of the page on the other side. And the element of area is always perpendicular to the area and away from it, so the element of area dA, this red stripe, will be oriented out of the page towards us. We can rewrite then the flux as the magnitude of the magnetic field is μ0I over 2 pi x. So we write the dot product as the magnitude of the first vector multiplied by the magnitude of the second vector. And for us, the element of area is the base of this area, which is dx, multiplied by the height, which is y. And don't forget that because you have a dot product, you also have to take into consideration the angle between the two vectors. And for us, the angle is 180 degrees. Magnetic field goes in, element of area comes out, and this cosine of 180 has a value of -1. Now, if you look at this integral, μ0 is a constant, current is a constant, 2 pi is a constant, y, the height of this area, is 10 centimeters and is a constant. So everything goes out of the integral, minus μ0I y divided by 2 pi, and what we have left under the integral is dx over x. Now, what are the limits of integration? Well, we can choose this area here on the left side of the rectangle, and that would be 2 centimeters from the wire, or we can choose it anywhere in between up to the right side of this loop, which is 5 centimeters from the left side or 7 centimeters from the wire. So our limits of integration will be from the 2 centimeters on the left, or 0.02 meters, to the 7 centimeters to the right, or 0.07 meters. Now, integral of dx over x is a very simple integral. It's nothing else than natural log of x. So the flux will be equal to μ0Iy divided by 2 pi multiplied by natural log of x between the limits of integration 0.02 meters and 0.07. All we have to do is replace the values given by the problem. μ0 is 4 pi times 10 to minus 7. The current is 20 amps. The height y of the area we have chosen is 10 centimeters or 0.1 meters divided by 2 pi times natural log of 0.07 divided by 0.02. That's when you put in the upper and lower limits of integration. Using a calculator, we obtain that the flux through this rectangular loop is -5 times 10 to -7 Webers. What does it mean that the flux is negative? It means that the field lines in this rectangular loop are actually going in instead of coming out. That's what negative flux means. And that agrees with the direction of the magnetic field that we have actually identified.